In this video, we're going to define wettability in terms of capillary pressure. We're going to define some terms, and we're going to show capillary pressure cycles. So in fact, let's go straight to capillary pressure. Now that we know that we can have capillary pressures that are both positive and negative. So let's draw here a nice large diagram. This is the capillary pressure, and just to remember, this is the pressure in phase 2 minus the pressure in phase 1. We're going to put 0 here, so we're going to put the axis like this. This is going to be, as we traditionally show it, the saturation in phase 1. This is a value of 1, and this is a value of 0. The first cycle that we've looked at is primary drainage. Now, I'm not going to say too much about primary drainage, so I'm going to try and just do it as a dotted line so that it doesn't distract us with the other cycles that are coming. But what happens is you have a steep rise until you can enter the porous medium. This is an invasion percolation process. This PC entry, which I'll introduce here, is in fact the capillary pressure at which you reach the percolation threshold for an invasion percolation process. We then, as we know, get a rapid change in saturation, and we're going to end up asymptotically here like that. So we're going to draw my primary drainage like this, and I will try and remove an other dashed line. Okay. So that's my primary drainage. Drew this. This is primary drainage. Okay. I'm now going to re-inject or reintroduce phase 1 into the pore space. But now what I'm going to do is I'm going to consider a general case which is mixed wet. We've looked at a totally water wet case where everything is at a positive capillary pressure and we trap some material and the capillary pressure goes down to 0. But now we're looking at a mixed wet case, so we have a water wet regions and hydrophobic regions. So here is going to be my residual saturation, and this is S2R. So this is the residual saturation S2R. And this now is achieved not at a 0 capillary pressure, but when I go down to a large negative capillary pressure. So what does the capillary pressure look like? We know that the capillary pressures in an imbibition process are lower. If it's mixed wet, it will then, here it's filling the water wet regions of the pore space. Here it's filling the hydrophobic or the oil wet regions of the pore space, and the capillary pressure is negative. So let's make that very clear. This is a positive value of capillary pressure. This is a negative. Positive represents phase 2 being non-wetting, phase 1 being wetting. But after a wettability alteration, negative capillary pressures represent the displacement in regions of the pore space where now phase 1 is non-wetting and phase 2 in comparison is the wetting phase. Okay? Okay. We will call this saturation, where the capillary pressure reaches 0, which is essentially the division between water wet and oil wet or hydrophobic regions, as S1 star. Right, there's no particular reason for that. I'm just labeling it how I want. Okay. Now we can consider another process, which is where I reintroduce phase 2 back into the porous medium. So I could re-inject oil or I could re-inject gas. You can imagine this process particularly for hydrogen storage in the subsurface. Hydrogen moves into the pore space, fills the rock, that's primary drainage. Then I withdraw hydrogen, that gets displaced by water, and then I'm going to inject hydrogen because remember I'm storing hydrogen for use as an energy store, so I'm both injecting and withdrawing it. So now we could have a process where we go back up, and I'm going to draw it first, and then we can describe what it shows. something like this. And again, I'm going to need to quickly get rid of the extraneous pieces here. So we can have a process now where when we reintroduce phase 2 into the porous medium, to begin with, I said there's some regions that are hydrophobic, so phase 2 is the wetting phase. So we get essentially an imbibition process of phase 2. So that's at a negative capillary pressure because actually phase 2 is at a lower pressure than phase 1. It wants to be in the pore space. It likes the pore space. It's oily. It likes it. Okay. And we get to a saturation here, which I'm going to call 1 minus S2 star, where S2 star is then the amount essentially of spontaneous imbibition of phase 2. Okay. Now, so this is what basically hysteresis loop looks like. Okay. We have primary drainage. We then have basically an imbibition process followed by actually forcing phase 1 into the pore space until we reach the residual saturation, the collapse of the layers that we described in the previous video. And then if we reintroduce phase 2, we actually have some imbibition of phase 2. Phase 2, the gas or the oil actually goes in spontaneously. Okay, and then we have to force it in to get back to the original saturation. And then we can do continued loops like this. Now, what do we call these various stages of displacement? And that's where there's often, I think, sloppy terminology, particularly in the oil literature. This is a primary drainage process because when we first introduce the oil or gas into the pore space, it is, in almost all cases, the non-wetting phase. But then, rather sillily, we describe this process as imbibition. But it isn't an imbibition process. This is an imbibition process, but this isn't. Right? This is where the water, phase 1, is non-wetting. So how do we define these? Well, what I would call this is imbibition. But just to make that clear, because sometimes people still confuse, imbibition is just water flooding. No, it isn't. This is spontaneous imbibition. So, now, the spontaneous here is a little bit redundant. In previous videos, I've talked about imbibition. Now I've introduced spontaneous imbibition. Oh, are they different? It's something subtle. No. Imbibition is imbibition is imbibition. It's where a wetting phase displaces a non-wetting phase. However, because of the confusion in the literature, we're going to put this extra qualifier, okay? Spontaneous imbibition. Right? It doesn't mean anything different, but now it's very clear for everyone and there's no ambiguity. So spontaneous imbibition is the displacement of phase 2 by phase 1 at a positive capillary pressure. So we go from the initial saturation here to this S1 star. And obviously, if we're more strongly water wet, S1 star goes towards the residual. If we're more strongly oil wet or hydrophobic, we're going to get more displacement that's negative, and S1 star will move towards S1R. Okay, and we can see anything in that range. So what do we call here? Well, that's technically it's a drainage process, but if you say it's drainage with water, people again just are in a muddle. So let's call it something that is still correct. This is basically forced water flood or forced injection of phase 1, right? Which is normally water. Okay, so this is forced. And what do I mean by forced? I mean I have to have the water at a higher pressure than phase 2. Than the oil or gas. I have to push it in, okay? I have to pump with a positive pressure and whack it in. Whereas spontaneous imbibition is where actually the pressure in the water is lower than the ambient pressure or the pressure in the fluid in the porous medium. So like a cloth, water soaks in. I don't have to push the water in, it soaks up spontaneously. Okay, then what do we call this region here? Again, this is technically imbibition, but to call it imbibition is going to be very confusing. So this we call spontaneous, right? So we use this displacement of phase 1 by phase 2. So this is a bit clumsy. So this would be spontaneous displacement of water by oil, or spontaneous displacement of water by gas. Okay, and then the last one here, this one, okay, this is a forced displacement, but actually when we're talking about oil or gas, people are quite familiar with its forced. We call that drainage. That's fine, that's correct. So this will be secondary drainage, right? Because it's not the first drainage, it's the second drainage process, and this is secondary drainage of phase 2, right? So just to be precise. So primary drainage is of phase 2. That's the first time phase 2 goes into the porous medium. This is the oil or gas for moving in for the first time, and this is where I do it again, and this is a forced displacement. Okay, so this is, in general, what a capillary pressure cycle looks like. And this primary process and a secondary process, and then the phase 2 is reintroduced, and then you're in this sort of hysteresis loop. Now, you might say, whoa, well, why am I sure? Why is the pink always above the blue, and why is it below the orange? Just think about it carefully in terms of the displacement processes. We already said we have capillary pressure hysteresis because there's contact angle hysteresis. Advancing and receding angles can be different. And we've also said, well, there's a wettability alteration, which is why these curves are different from this function. And there are different displacement processes and trapping. Okay, so remember now that there's trapping, different displacement process. If you just go through it carefully on physical grounds, the blue is below both the pink and the orange, regardless of what processes you're considering. Okay, now let's consider how we quantify wettability in terms of capillary pressure. So at the pore scale, fundamentally wettability is determined by the distribution of contact angles. With high-resolution X-ray imaging, we can see inside rocks, and we can indeed measure, or at least estimate, that contact angle distribution, which is very useful for characterization and for modeling. But that does require sophisticated equipment, and is still something that's very much a research topic. So how do we deal with this on a macroscopic level? Well, actually, that's quite straightforward. We have what's called the Amott wettability indices, and that's named after Amott. And what he designed was an experimental protocol as follows. He started actually with a porous medium, a rock, that was at water flood residual oil. Could be residual gas, but it's the residual of phase 2. He then basically put that rock, dumped it in a bath full of phase 2, which basically is oil in his case, right? So you have this rock, you just put it in a bath of oil. You wait, and does the oil spontaneously imbibe? How do you know how much imbibes? You don't need sophisticated X-ray apparatus. You basically just weigh the rock. As oil imbibes and water comes out, actually the rock becomes more buoyant in the oil, and so the apparent weight actually goes down, and you can very accurately measure how much basically did you go from there to there. Then you take the sample out, and you get a pump, and you whack the pump up, and you pump in as much oil as you can to get to this point. Then you take the rock out, now it's containing mainly oil. You put it in a bath full of water. You see how much spontaneously imbibes. As it does that, you can weigh it, and it gets heavier. Then you get to this point, then you take it out, and you have a pump with water, and you whack the water in until you get to this point. So basically what you do is you can do these cycles, and they're actually relatively straightforward to measure, and you can actually get a good measurement in a rock sample of essentially these points, the residual, this point, and this point. And you can do this either by mass balance or by volume balance. Okay, so let's imagine that you've done that experiment, and I'm not going to say too much about the experimental protocol, but it's something that's quite standard, certainly in the oil industry. So how do we define our wettability indices? So we define a water index, which is the amount of spontaneous imbibition. So that's the saturation change during the spontaneous imbibition process. So it's S1 star minus S1I divided by the total amount of displacement that we have, okay? Which is 1 minus S1I minus S2R, because this is the total amount of displacement. Okay, so that's the wettability index for water, and we can have the wettability index for oil or phase 2. So this is really phase 2 because it can be a gas, and this can be water, but that's phase 1. So for phase 2, it's the amount of spontaneous imbibition of phase 2, which is going from there to there, which is S2 star minus S2 residual. So it's the change in S2, right, due to spontaneous displacement divided by the total amount, which is the same in both cases. Okay, so both of these indices, both of the indices are between 1 and 0. Okay? So what that represents is if the water index is positive, then we have some water-wet regions. If the oil index is positive, we have some oil-wet regions or gas-wet regions. So if we have I1 and I1 and I2 are both greater than 0, we have a medium that's mixed wet. If we have just I1 is greater than 0 and I2 is equal to 0, there's no spontaneous imbibition of phase 2, then this is clearly water wet or 1 wet, right? Phase 1 is wetting. If on the other hand we have I1 is 0, so there's no spontaneous imbibition, we go straight to a negative capillary pressure, but I2 is greater than 0, then that's wetting to phase 2, so we could call that oil or gas wet, depending on what the phase is. Sometimes we can use the word hydrophobic, which means hates water. Water wet, if you want to use a Greek word, it is hydrophilic, which means it loves water. So that's what these wettability indices mean, so it doesn't get confusing. Right, this one is that one, this one is the water wet case, and this one is the hydrophobic case. Okay, so that's the definitions. Very clear, very precise actually, straightforward, relatively speaking, to measure. Amott, by the way, was one of the few researchers who did understand wettability, and again in a model thinking imbibition was when I was pushing water in. He knew the distinction, and so other people should stick to it. We knew how to define wettability properly, and this was in the 1950s. Why have we gone backwards in the last 70 years? No idea, right? So stick to the proper definitions. Final thing, unfortunately, at the time that Amott did his experiments, this idea of mixed wettability was not really well understood. It wasn't until the 1980s that people really appreciated that you could have regions of the pore space, some of which were hydrophilic and some were hydrophobic. You had a mixture of wettabilities. And you see this not just in rocks, but you can see them in electrochemical devices as well, where you have carbon fibers that are naturally water wet, but have a partial plastic coating as a binder. So you have a mix of wettabilities. So it's actually a very typical circumstance, but at the time that wasn't understood. People assumed there was one contact angle in the pore space, so that contact angle was either less than 90 degrees, in which case it was obviously water wet, or it was greater than 90 degrees, in which case it was oil wet. Okay, and 90 degrees was sort of in between, and that was intermediate wet. So if you assume that mixed wettability is not possible axiomatically, then one of these I's has to be 0. You can't spontaneously imbibe both. So what was introduced as a backward step, I'm introducing it to tell you not to use it, was what's known as the Amott-Harvey index. And I'll just write this down, which is IAH was the water index minus the oil, or if we want to do it in more general, it's I1 minus I2. Now the Amott-Harvey index is just the difference, because it says, well, if one of these indices is 0, we only need one number. So if it's +1, it's strongly water wet. If it's -1, it's strongly hydrophobic. And if it's 0, it's intermediate. The problem with this is, in fact, it's a loss of information. Most cases are mixed wet. So if your Amott-Harvey index is around 0, Is it because all the contact angles are uniformly about 90 degrees and you're not getting any spontaneous imbibition of either phase? Or is it because you've got a mixture of very strongly water wet soaking up the water and very strongly oil or gas wet soaking up that phase? That information is lost. So for those people who are actually doing these measurements or doing this analysis, quote both of those indices because they're both, in most cases, positive. And don't take the difference and then make some random speculations based on what you've read and become very qualitative. Just quote the numbers. Okay, this concludes now the description of displacement and capillary pressure. But what we haven't introduced yet is actually how the fluids flow through the pore space. And that's going to come next in the videos.